today we're going to have a look at using this ATORCH DL24P load device to kind of assess a couple of power bricks. So we've got, I've got a couple of these different bricks that came with iPhones. There's some rumor about how the one with a green dot here is a little better than the regular one, so we'll try to figure out why exactly that's the case. And we'll have a look at this brick here that came with a Maxtor One Touch, but it's a certified. You can see under the tape there, it's got all kinds of Underwriter Labs and ETL and various certifications where this device can be used all over the world. So it's got a lot of ratings there, so it's a good device. And then I've got a kind of an off-brand, more modern. This is a USB-C device, so we'll have to kind of have a look at whether or not we need to introduce some power delivery triggers to make all of this work. So I'm going to have a look at these sorts of things to see exactly how we can test some of these units using this this ATORCH load. So in order to do that, most of the time is going to be spent zoomed in on the control panel in order to be able to see exactly what's happening. So let's do that now. Let's zoom in. Okay, so we're zoomed in, and in general, for testing these devices, what we want to do is we generally want to make use of testing using one of two modes. This device has 4 modes, and there's a video that shows the different kinds of modes. But we want to use either constant current mode or constant power mode. They're the ones that are sort of easiest to understand and easiest to relate to when it comes to these power bricks. So I'm going to do most of this, in fact I'm going to do almost all of it with constant current mode. You can see that right now the target current is set to 0, but we'll change that in a minute. So I've got the power brick and I've plugged it in, and we can see that right now it's producing a voltage of 5 volts. And these devices are spec'd to produce 5 volts at up to 1 amp. So let's put 1 amp inside here. Okay, so we'll bump that up. Okay, so we've got a 1 amp. This is a target 1 amp load that we're going to put on, and we'll turn that on. And right away we can see that it's doing a pretty good job of keeping the load at 1 amp. The voltage is pretty stable there, and the power is pretty stable there. So when we're operating within the standard operational parameters of what the unit is spec'd for, we should see some pretty stable operation. Where this starts to go a little bit off the rails is when we start to go out of spec. So certainly if we can draw 1 amp in a stable fashion, drawing less than 1 amp is not going to be all that interesting. So let's start cranking up the current draw here and see what happens. So we're going to go from 1 amp to 1.1 amp. Okay, we do that. And you can see not a lot has changed there. We're still drawing 4.8 volts. We're kind of pulling the 1.1 amp that was requested. The power is staying stable, or sorry, the power's gone up. And let's now, okay, so remember that was 4.8 volts. We're going to go up another 100 milliamps. Okay, so now we're at 1.3. Once again, so the voltage is still pretty stable. We're asking for 1.2 amps. The power is coming along pretty well. The key thing to note here is the voltage. So pay attention as we kind of ratchet this up again. We're going to go to 1.3. Okay, now at 1.3 amps, you can see we're getting a error message there, and it can't really maintain a stable configuration. So the power brick can't really maintain a stable 1.3 amp output the voltage kind of drops off a bit of a cliff when it tries to do that. So go back down to 1.2, and once again we can see it kind of settles back in to 4.8 volts and the 1.2 amps that we're requesting. So you can see that tells us that the upper limit capability of this particular power brick is somewhere around 1.2 amps, and the total power output that it can generate is somewhere around 5.7 watts. Now, one of the things that we could try is we could try putting this into a constant power situation, but it'll just end up doing more or less the same thing because the unit can't get itself the unit can't get itself to a configuration where it can pull more power without having the voltage plummet, which ends up producing less power. And so we can see that 1.3 amps is clearly beyond the ability of this little module to deliver. So now let's stop that. Let's go back down to 1.1 amp. So now that was the one without the green dot. So now I've got the one with the green dot. So let's switch those around and see what happens. So I'm unplugging it from the one. You can see the voltage goes to 0. I'm plugging it into the other one. And I mean, one thing we see, which isn't a big deal, but we do see now that the voltage is a little bit higher, not enough to make any difference. Or any important difference. So let's start out here at 1 amp. Let's turn it on. We can see everything is fine. Okay. Let's do what we did before. 1.1 amp. Everything is fine. 1.2 amps. Everything is fine. 1.3. Okay, now you'll see this one is not sort of falling off the cliff at 1.3, so it's still operating. It's almost able to, or it's, for most purposes, it's able to produce 1.3 amps. But you'll notice that the voltage dropped off. So at 1.2, we were at 4.7 volts, 4.78. At 1.3, well, still 4.76. That's a lower voltage than the other one was producing. But now if we go to 1.4, you can see that's where there's been a big fall off. Now, the unit hasn't kind of totally gone crazy on us, but you can see that we had a big drop off in voltage between these. So from 1.3 amps at 4.7 volts, there's sort of, now we're around 4.4 volts. So there's about a 300 millivolt drop as we try to push the current to 1.4 amps. And of course, if we go to 1.5, an even bigger drop as well. So now, interestingly enough, even though we're pulling the 1.5 amps of current, and we're not really producing much more power. And I'll tell you, I don't actually feel much of a temperature increase on the brick either. But the circuitry on the brick, even though we're trying to say pull more current, the circuitry is basically just responding to that by dropping the voltage down. And so in the end, the voltage drop ends up producing, we end up with the same amount of power overall. So we can see a kind of a clear difference in the behavior of the two different power bricks. The one brick just totally gives up, in a sense, when the power draw exceeds what it can produce, whereas this one, well, it satisfies the current request, but it's not able to do that while maintaining a constant voltage, and whatever we're plugging it into probably needs a certain voltage level in order to operate. We can kind of go even higher, and at some point you can see that it just kind of starts to get really, really funky, where it's just not even reasonably within the operating parameters. But just a totally different behavior than the first power brick. So let's stop torturing the unit, turn that off. Okay, now let's switch from those two bricks. So we now understand a little bit better about what the difference is between the brick with the green dot and the brick with no green dot. Let's switch over to this unit. Okay, so this produces 12 volts. It can go up to 2.5 amps. And let's see. Well, first let's test that it can produce that in a stable fashion, and let's see how far beyond its rated maximum we can go. So we've got the power brick plugged in there in the barrel connector. It's not turned on yet. It had been turned on just before this video, and you can see it's still draining. There's still a little bit of voltage left behind. So that just goes to show that that these units can store some residual power. And so even though you've turned them off, you know, sometimes you do need to be careful, especially right after you've turned them off. They can, unless they have some sort of a bleeding circuit to bleed away the power, they can have some power in them for quite some time. So now let's turn them on, turn this on. So you can see that the voltage comes in, and we're seeing about 12.3 volts, which is typically, you know, what we expect. There's always a little bit of variation in the voltage on these devices, but we haven't engaged any load yet. Now, I've set this to 2 amps to begin with. The brick is rated for at least 2.5 amps, so we shouldn't see anything too surprising. But this is just to give us a baseline. Okay, now I'm going to have to make sure I talk louder, because of course at 12 volts and 2 amps, we're generating around, as you see here, almost 24 watts of power. And so that means that we've got to do some serious cooling. And so the fan has kicked in along with the coloration, if you can see that on the screen, in order to try to keep the circuitry that is generating the load, in order to keep that cool and not melt down. We can see here the internal temperature has kind of come up to 27 degrees centigrade. I don't have the external temperature hooked up, but we can see the internal temperature. So now let's start to move the current load up a little bit. So we're going to go from 2 amps up to 2.5 amps. So we should see the power start to rise as well. And notice the voltage did come down a little bit, but once again, pretty close to 12 volts, so not a big deal there. Okay, so we're now at the rated max for the power unit. So we're at 2.5 amps. And the voltage, once again, it's come down a little bit, but nothing really that will make a big difference. So we're down to it's effectively 11.8, 11.9 volts if we round it properly. So not a big deal. And the unit is able to operate stably. It's delivering close to 30 watts of power. So that's what we expect out of the power brick. Now, or power supply. Now, what happens as we start to raise the power here? Okay, so the first thing we'll start to notice, is as we go a little bit over, we're not going to see too much variation, because all of these units can handle a little bit of a draw that is a little bit beyond their specs. That's just good engineering practice. I would be totally shocked if the engineers that designed this unit to begin with didn't put in a little bit of buffer capacity. So let's kind of keep in mind that the key things to look at are the voltage, because as we saw with the smaller power bricks, the voltage is what is going to be the first giveaway for whether we're exceeding the ability of the unit to operate, because there'll be a pretty massive voltage drop at some point. Okay, so we're really, right now, we're 11.8, 11.9 volts. We'll go up to 2.6. Once again, I'm just going to start going up, because until this voltage really starts to vary, there's nothing really to write home about. 2.7, 2.8. You can see that the voltage dropped a little more significantly there. 2.9, starting to have more of an effect. 3, okay, we're down to 11 volts. Well, 11.7 volts, sorry. 3.1, 3.2, and 3, and 4. And that's where you saw a big drop there. So we went from 11.7 to 11.5, not just a very little, drop. Right? If we go back here, we're 11.7. When we go to 3.4, we come down to 11.5. So we're losing about 150, 200 millivolts. If we go a little higher to 3.5, an even bigger drop there. And so that's typically what happens as we reach the true edge of where these power supplies can operate, the true limits of these power supplies. The voltage begins to sort of decrease quite sharply, right? So here we're 11.1. If I go back to 3.4, it goes back to 11.5, big difference. 3.5, it goes up to 11.7, a fairly big difference. If I go to 3.2, it's still 11.7, not a huge drop. 3.1, 11.7, not a huge change there. 3.0, still 11.7, not a huge change. So you can see while this is operating within its inability, within tolerances, the real tolerances, let's say, the voltage drops as I push the current beyond a spec level is not too bad. But when we get to that threshold, the voltage starts to really drop. Now if I go to 3.6, we can see it's now dropped to 10 volts, 10.7, 3.7. Okay, and the thing to notice is as we're doing that, we're not really generating much more power here. We're pulling more current, or we have a higher current load, but we're not generating more power. So I'm going to go up to, we're about 38 watts now. I'm going to go up to 4 amps. Okay, once again, we've kind of lost a little bit of power. We're at 37.5 watts, but now the voltage is down to 9.7. We are drawing the 4 amps, but with the drop in voltage, the amount of power we're actually able to pull out of the unit isn't really increasing. So the maximum amount of power that we can see here was about 39 watts that kicked in at about 3.5 amps. And of course, the rated amount of power would be about 30 amps. So it's possible to get a little bit more power, right? So we're going from about 30 amps to almost 40 amps. So about a 10 amp delta there. That's about what, a 33% boost in the amount of power that it can generate beyond spec. So pretty good overall, but it really does give us a sense of where the tolerances are for these units. Now, the other thing that is important with these power bricks is to run them at their rated load, their maximum load. So this one, the max load is 2.5 amps. And what we would want to do is we'd want to run this test for a few hours, because of course that's what's going to happen when it's plugged into whatever device that it's being used for. So we would want to run it for a few hours and make sure that over those hours it hasn't really cut out or melted down, because those are the things that sort of happen if the circuitry degrades. It tends to get really, really hot, and the system basically starts to fail. So that's the other piece. And I'm not going to do that with this unit because I know this one works. It's been in service for a long time, but we are going to... If you found this video useful, please give it a thumbs up and please subscribe to my channel. Thanks for watching.